Welcome to section 3.2, calculus of vector valued functions. So I'm going to give you the short version right now. To perform calculus on vector valued functions, you're going to do it component wise. So if you want the derivative of a vector valued function, you're going to take the derivative of each piece. If you want the integral of a vector valued function, you're going to integrate each piece. So it's that easy. And so now I'm going to spend 20 minutes giving you the long version. Okay, so find the tangent vector for r of t. The tangent vector is going to be r prime of t. R prime of t. So we're going to take the derivative. Now this is negative 3, 5t all to the 1/2. So to take the derivative, we're going to bring the 1/2 down. We're going to leave the inside fixed. New exponent is negative 1/2. And then we're going to multiply by the derivative of the inside, which is 5. And then for the next piece, remember for the derivative of ln of u of t, you want u prime over u. And so this will be negative 2 times the derivative of ln 5t is 5 over 5t. 5 over 5t, which is 1 over t, because the 5's cancel. All right, and so let's do a little bit of cleanup. This is negative 15 on top, 2 square root of 5t on the bottom, and then negative 2 over t. Okay, find the unit tangent vector, big T of 0, for this function at t equals 0. So a couple of different things here. First, we're going to evaluate the derivative at 0. Second, we want a unit vector, so we're going to have to divide through by its length. So let's start with r prime of t. 4t cubed. Then for the middle part, we bring a 2 down, negative 4e to the 2t. And then for the last part, we get cos of negative 4t times the derivative of the inside, which is negative 4. So negative 4 cos of negative 4t. And now let's compute r prime of 0. It's going to be 0, negative 4, comma, cosine of 0 is 1, so negative 4. So that is a tangent vector at t equals 0, but we want it to be unit, so we want to find its length. The length of r prime of 0 is the square root of negative 4 squared plus negative 4 squared. 16 plus 16 is 32. We're going to call this vector big T of 0, and that's r prime of 0 divided by its length, which is 0, negative 4 over the square root of 32, negative 4 over the square root of 32. Okay, and so this problem is a practice problem, so I want you to pause the video, try it out. I think I put the solution at the end. I did, so you can check to see if you did it right or not. Find the value of t where this curve is perpendicular to its tangent vector. Okay, so that might be a little bit confusing to you because you might say, well, wait a minute, a curve can't be perpendicular to its tangent vector. But remember how we graph a curve? We plot the endpoints. And so if you're looking, let me just simplify it to a 2D version. Here's a circle, cos t, sine t. Okay, so I'm going to plot t equals 0. That gives me x is 0, x is 1, y is 0. So there is the vector that gives me this point. Now the tangent to this curve goes like this. So the tangent is perpendicular to the vector on the curve. So it does make sense. How to draw a tangent vector. So we like to draw our tangent vectors on the curve so they actually look tangent. So here's a curve, t, 2t squared minus 1. Draw the vector r of 1 in standard position. That means base at the origin. base at 0, 0. So let's find r of 1, not r prime of 1, r of 1. That would be 1, comma 1. So I start at the origin and I go to 1, 1. And the end of that vector should lie on the curve because that's how you get the curve, by plotting the endpoints of each vector. So there's my r of 1 in standard position. Now I'm going to find r prime of t, 1, comma 4t, and I'm going to compute r prime of 1, 1, comma 4. So to make this actually look, if I graph this in standard position, it won't look tangent to the curve at all. But if I start right here at the end point of r of 1, which is 1, comma 1, and now I graph this vector, so I'm going to go 1 unit over to the right and 4 up. So I go 1 over and 1, 2, 3, 4 up. I end up there and I draw the vector like that, then it looks like it's actually tangent. Well, it should be a straight line, but it's not. A little too much coffee. It's not exactly straight, but you get the idea. Okay, tangent lines. So tangent lines are just extensions of tangent vectors. If I wanted the tangent line, I would just take the line that passes through that vector. It passes through 1, comma 1, and the direction vector of the tangent line would be 1, comma 4. So recall, to get parametric equations for a line, you want x naught plus at, y naught plus bt, z naught plus ct, where x naught, y naught, z naught is on the curve, and abc is the direction vector for the line. And so we know exactly how to do this. The only thing different here is our direction vector is going to be the derivative at t naught, just like we did above. We take the derivative at a certain point, that will give us our direction vector. So let's do an example. Find parametric equations for the tangent line to this curve at pi over 4. So first of all, we need our point P. P is going to be r of pi over 4. And I'm going to use pointy brackets even though I'm thinking of it as a point, not a vector. So cosine of pi over 4 times 2 is pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. And then I get ln of pi over 2. Okay, and so you can think of that as if you want, as a point, 0, 1, ln of pi over 2. And that's our x naught, y naught, z naught. Okay, now we need our direction vector. So first we need the derivative, r prime of t. So we're going to use the chain rule. Derivative of cosine is negative, so negative 2 sine 2t, 2 cosine 2t, 1 over t. And now my direction vector is going to be v, which is r prime at pi over 4. So this is negative 2, 0, and 1 over pi over 4 is 4 over pi. So this is my A, B, C. So now I just put it all together. X is x naught, which is 0, plus A, which is negative 2 times t. So negative 2t. Y is y naught, which is 1, plus bt. B is 0, so plus 0. So I'm not going to write plus 0. Z is ln of pi over 2 plus ct. C is pi over 4. Sorry, 4 over pi t. All right, and there you go. Okay, so you should pause the video and do this one. It's pretty straightforward, and I have the answer at the end. Properties of derivatives. Well, what's interesting? No surprise on this one or this one. Notice that the dot product one looks a lot like the product rule. The derivative of u dot v is u prime dot v plus u dot v prime. Similar for cross. The one I'm interested in is constant length vectors. If u dot u is a constant, remember u dot u is the length of u squared. So if the length of u squared is constant, then the length of u is constant. So an example of a constant length vector would be vectors on a circle. A cosine t, a sine t. All of those vectors have constant length, and the length is a. This is a circle of radius a. And what it says is if you have a constant length vector, then the position vector is perpendicular to the tangent vector, because the tangent vector dot the position vector is 0. That means they're perpendicular. And sure enough, if I find the tangent vector at any point on this circle, it will indeed be perpendicular to the position vector. Okay, integrals of vector valued functions. Again, everything's going to be component-wise. So there are no surprises here. Let's integrate. So this is good practice. Integrating integral of r of t dt is going to be the integral of 3t plus 5 to the 1/2 dt, comma, the integral of 1 over t minus 1 dt, comma, the integral of -4 cos 2t dt. Now for this one, we could do a u sub. U is 3t plus 5. Du is 3 dt. So 1/3 du is dt. So this first one, I'll do my scrap paper over here. The first one is 1/3 the integral of u to the 1/2 du. That'll give us 2 over 9 u to the 3/2 plus c. So this is going to be 2 over 9, 3t plus 5 to the 3/2. I'm going to hold off on my plus c and add my constants as a separate vector. So I'm just going to put comma here. Next one, u sub, u is t minus 1. So this is natural log absolute value t minus 1. And the last one's a straight up Bible formula. Bring a 1/2 out, and that gives us -2 sine 2t. Plus, I can add the constant in a couple different ways. I can write big C, where this is a vector, because you can only add a vector to a vector. You can't add a number to a vector. I like to make it a little more explicit. C1, C2, C3, like that. In your homework, I noticed they have you enter this answer, and then they'll put the C in for you. They'll say plus, and they'll think of this as a vector. They'll say big C. But I want you to realize big C isn't a number, it's a vector. And then some people, just to belabor a point, some people actually like to put the C in to the actual vector, 3t plus 5 to the 3/2 plus C1, comma, ln t minus 1 plus C2, -2 sine 2t plus C3. They're all correct. They're all the same thing. Now, for solving an initial value problem, that's actually what I'm going to do. I'm going to put the c's in when I integrate. So solving an initial value problem, you're given a derivative, you're given an initial value, you have to find the function. So I've started us out. We need to find r, we need to integrate these two functions. So that's going to be Bible formula, -1/2 e to the -2t. And I'm going to put my constant here, comma, ln absolute t plus 1 plus c2. Okay, r of 0 is 1, 0. So r of 0 is 1, 0 on the one hand. On the other hand, it's this function when I put t equals 0 in. So put t equals 0 in, and we get -1/2 plus c1, and then comma, ln of 1 is 0, so c2. So this gives me two equations to solve. 1 equals -1/2 plus c1, and 0 equals c2. I can solve 0 equals C2. That's pretty easy. And this one is also pretty easy. C1 is 3/2. So then you just go back. So step 1 is to find R. Let me make some steps here. Step 2 is to find C. So R, find C, and step 3 is to put steps 1 and 2 together. So we have our answer here, but it's got C's in it, but we found the C's. So now we give our final answer, -1/2 e to the -2t plus C1 is 3/2, comma, and then ln absolute t plus 1 plus 0. So there's our final answer. So I think when you're solving an initial value problem, it's easier to embed your constants right into your R of t rather than leaving them out here. Okay, so it's a pretty straightforward section, and then we'll do some more things next time. It's a short chapter, so we're almost done with this chapter.